And now to complete the presentation this week, we will talk about the implementation of multilayer perceptron in scikit-learn. So multilayer perceptron is available in scikit-learn. This includes some, but not all, of the advances we find in deep neural networks. Of course, next week we will talk about deep neural networks, which are, I would say, an extension of multilayer perceptron with new models. So scikit-learn includes several of these advances that are usable with multilayer perceptron, but these are relatively rigid models. These are not easy to be customized. We need to stick to the basic model. There are no GPU acceleration, so it is much more slower to train on CPU than GPU with neural networks. And we are not able to make use of GPUs with the current implementation of MLP multilayer perceptron in scikit-learn. So we have the class Mlp Classifier, which is a MLP multilayer perceptron for classification. It is relying on the cross entropy as error criterion, so it is not mean square error. It is cross entropy, which is the same criterion used for logistic regression. And we also have the regression version, MLP regressor. So it is a multilayer perceptron for regression, where we aim at minimizing the quadratic error with gradient-based methods. And these two models include a bunch of parameters, even though it is not customizable as we can get with PyTorch, for example. There are still many things we can modify in this implementation of MLPs, of multilayer perceptrons in scikit-learn. For example, we can simply adjust the number of neurons and on each layers with the hidden layer sizes. So in fact, it is like the number of hidden layers and the number of neurons in each of these layers. We also have the activation function that can be defined for things like sigmoid functions, linear functions, tanh, ReLU. By default, it is ReLU that is used. The solvers, we can use different type of solvers. The Casey-Newton LBFGS, which is basically kind of approximation of second order approaches, is possible, but we have a stochastic gradient descent or ADAM with some nice tricks to adapt the learning rate. By default, it is ADAM that is used, which is known to perform relatively well. There are some alpha to make regularization of the weights. We may want this in order to disable or keep the weights in the neural network to be low. We also have a batch size, so the training is done through many batches. Usually it's minimum between 200 and N. So basically, if you have a really small data set, we will use the full data set. But once the training set is over 200 samples, we will use many batches of 200 samples by default. We have an initial learning rate, which is adjusted. In fact, with ADAM, the learning rate is changed over time, but we can set the initial learning rate to some values. We also set the learning rate changes according to being constant or variance scaling, when we will reduce over time, or adaptive, which is a different rule, which are like different ways to adjust the learning rate, which are also different from what ADAM is doing. We also have the maximum number of epochs, which is set to 200. We also have a tolerance. This is used for the stop criterion, where we will stop learning if the gain is less than the tolerance for more than 2 epochs. And we have the momentum, for gradient descent, which is set by default to 0.9. So we have a great deal of momentum that is used in that training. And in terms of early stopping, this is used to say, do we stop when the error on validation set stop going down, when we see that we are stagnating or increasing. By default, it is disabled, but that's a good thing, I would say, to use in general to stop the training when we see that there are some stagnations on the validation set. And finally, there's the validation, not finally, but one of the last criterion that we present here is the validation fraction. So what is the proportion of the training set that is used for evaluating the generalization error in terms of early stopping? By default, it is 10% of the training set that is used as validation. Yeah, and that's it, finally. So these are different parameters available for MLP classifier and MLP regressor. There are some others available also. Like I said before, these give us a bunch of parameters to adjust the models, but still we are sticking to basic multi-layer perceptrons. If we want to use more fancy implementation of neural networks, if that's the thing with neural networks, we can do many different things. This is super general as models. We need to use other libraries like PyTorch, we will see later on in the course in the next weeks.